In this video, we're going to talk about one aspect of the derivative that's particularly important for real-life applications. So this is going to be the derivative as a rate of change, and it's section 3.6 of the text. So why don't you copy this down, press pause, copy this down, and I'll chart. All right, so we have covered these items before. The derivative of f at x is denoted f prime of x, and it can tell us one of many different things. It can tell us the slope of the line tangent to the graph of f at whatever x value we choose to plug in. It's also telling us the slope of the actual graph of f at whatever x value we choose to plug in. And then it's telling us the instantaneous rate of change of the function at that particular x value. That's what the slope of the function is. It's its instantaneous rate of change. And the way we calculate the derivative is we can either revert back to ye olde limit definition of the derivative, or if the function allows it, we might just use some of the differentiation rules or shortcuts that we've picked up, and you'll continue to pick up when you take 109, okay? So today, though, we're going to be focusing on this aspect or this piece of information that the derivative is telling us, the instantaneous rate of change of this quantity our function is telling us about. All right. Okay, so why don't you press pause and copy down the statement and the three questions we're going to answer. All right, so we are modeling the number of worldwide internet users, and our function is going to tell us the number of millions of internet users. So if the function says 12, that really means 12 million internet users. So we're modeling the number of internet users in millions from the year 2000 to the year 2015. And here's the function that models that number of users in millions, where t is telling us the number of years since 2000. And the output, P of t, is the number of millions of users. So let me do part B first, okay? Approximately how many internet users were there in 2011, okay? Well, so 2011 corresponds to a t value of 11. And if I want to know the number of internet users, that's what my function P of t is telling me. So the number of users in 2011 is going to be given by my function with t equals 11 plugged in. So let me plug that in. I got 6 times 11 squared plus 98 times 11 plus 431.2. All right, and I calculated that over on the sideboard that you can't see, and I got 2,235.2 million users. Or if you don't want to see the million, you can just say, well, 2,000 million is 2 billion. So 2,235.2, that's 2 million, and I need billion. All right, so I'd multiply this number 2,200 by 1 million, and I get that number of users, 2,235,200,000 viewers, internet users, okay? All right, so that was pretty simple. Plug in the population into the function and interpret the answer correctly. All right, well, let's go back to A then. Determine the average rate of growth of internet users from 2000 to 2011. Sorry, from 2005 to 2010. All right, well, 2005 would be t equals 5, and 2010 would be t equals 10. So the average rate of growth, that's going to be, well, how much did it grow over those 5 years? And then let's divide by the 5 years so we can get an average rate per year of growth. So this is going to say, I want to calculate the population of internet users, P of 10, minus P of 5, divided by 10 minus 5. This is our average rate of growth formula, the slope of our secant line formula, okay? All right, so if I calculate P of 10, it'd be 6 times 10 squared plus 98 times 10 plus 431.2. And then if I calculate P of 5, it'd be 6 times 5 squared plus 98 times 5 plus 431.2. I'm dividing all of that by 10 minus 5, which is 5, okay? All right, well, now I cranked all that numerator out and I divided by 5, and I got 188, okay? All right, and I should have some units on that. So this was millions of users in the numerator, and this was years in the denominator. So I think I have 188 million users per year. So between 2005 and 2010, the number of internet users is growing by about 188 million users per year. Expressed another way, I could say it's 188 million users per year. And it's growing. This rate is positive. So every year we're adding more people, about 188 million more people per year on average, okay? All right, so we've done problems like that before. Well, now we want to determine the instantaneous rate of growth of internet users in 2011. All right, well, first off, 2011 corresponds to t equals 11, okay? And the instantaneous rate of growth of users, well, that's the derivative of the number of users. So I need to calculate the derivative of p at 11, okay? All right, well, step one, let's calculate p prime of t, okay? All right, well, if I go in slow motion, I'm going to take the derivative of 6t squared plus 98t plus 431.2. I'm going to take the derivative of that, okay? And I know that addition doesn't bother me. I can just take the derivative of 6t squared, the derivative of 98t, and the derivative of 431.2, and then just add them together, all right? And I know the 6 in front of the t squared doesn't bother me. I can drag it out and multiply it by the derivative of t squared. And the 98 multiplied by the t, that constant 98, I can drag it out in front to multiply by the derivative of t. And then I also know that the derivative of any number, any constant, is always 0. So that last derivative goes to 0. Okay? Well, now the derivative of t squared, well, the power rule says drag your power 2 down in front, and your new power is going to be 2 minus 1. So that'd just be 1. There's my 98. The derivative of t, we know is just a 1. And then I got a 0 plus 0. So it looks like p prime of t is 12t plus 98. All right, well, now I'm after p prime at 11. So now I can plug in t equals 11 into my derivative. So this is 12 times 11 plus 98. And that gives me, what's 132? 230, right? So that's my unit of measure. But remember, this derivative, it comes from like a slope calculation. So the units in the numerator would be millions of users. And the units in the denominator was years. So millions of users per year. So in 2011, the number of internet users per year was growing at a rate of 230 million users per year. So in 2011, we're experiencing growth of about 230 million new users that year. On average, from 2005 to 2010, it was a bit less than that, okay? But the derivative tells us our instantaneous rate of change. Okay. Just let's just take one more peek at B. All right, so last example. Okay. So I'll let you copy this down. All right, so in this example, we have a function, and the situation is we got a drone flying around us. You know, we're standing still, got a remote, and drone's flying around us. And the distance in feet between myself and the drone after t seconds is given by this function, okay? And this function is only a good model of that distance for the first 15 seconds, okay? All All right, so how far from the drone, from you is the drone after 8 seconds? And then I've got some velocity questions. Okay. All right, well, how far from you is the drone after 8 seconds? Well, this function tells me how far away the drone is from me after t seconds. So here I'm simply after s of 8. So if I plug t in for 8 in the original function, I get 20 times 8 minus 8 squared. So I think I get 160, whoops-a-daisy, 8 squared. I get 160 minus 64, so I get 96, and the unit of measurement was feet. So after 8 seconds, the drone is 96 feet away from me, okay? All right, now what's the drone's velocity after 6 seconds? Well, velocity, this is the instantaneous rate of change of position or distance. Okay, so the instantaneous rate at which the distance is changing per second, that's the definition of velocity. So the velocity is equal to the derivative of s, of our distance function. So let's go ahead and calculate that derivative, okay? So s prime of t, I'm going to take the derivative of 20t minus t squared. And one of the rules we learned said that, well, subtraction doesn't bother us. I can just take the derivative of 20t and subtract the derivative of t squared. Okay? And 20 times t is easy to handle. The constant 20 being multiplied by t can just get dragged out in front. And then I just focus on the derivative of t. Oops. We got a derivative sign there too. All right, so the 20 can get dragged out of the derivative. And then the derivative of t squared by the power rule, that's the power 2 comes down in front. And then I have t to the 1 less power, so the 2 minus 1 power, or to the first power. And then I believe the derivative of t is just a 1. So I think my derivative, s prime of t, is 20 minus 2t. Okay. All right. So in general, I now have the derivative. So I could now find the velocity at any time I like. They're interested in the velocity at time 6. So s prime of 6 would be 20 minus 2 times 6. So that's 20 minus 12, so that's 8. Okay? All right. Now remember, the derivative comes from that limit h approaches 0, s of t plus h, s of t all over h. S of t is measured in feet, and my horizontal, my t's and h's, are being measured in seconds. So the unit on 8 is 8 feet per second. Okay? All right, so you'll note that this number is a positive 8 feet per second. That would mean that the drone is getting further away from you. The distance is increasing. So if you imagine the distance graph, the curve, the slope is positive 8. So the distance graph is increasing. So the drone is getting further away from you. The distance is getting further away. So drone moving away from you at t equals 6 seconds at velocity 8 feet per second. So it's getting further away, okay? All right, well, now, same question, what's the drone's velocity after 15 seconds? So here we want s prime, the derivative, at time 15. Now, I've already calculated s prime of t. That was 20 minus 2t. So I'm just going to use that and plug in 15 for t. So this would be 20 minus 2 times 15. So that's 20 minus 30. So that would be negative 10 feet per second. Huh. So I have a negative velocity, and that's kind of curious, but imagine I showed you this graph of s of t, and it's a parabola opening downward. And to have a negative derivative, that would mean the graph has a negative slope. So maybe that's 15 right there, and this is the graph of the original function S of t. We've got a negative slope. And this is distance. So it appears at this moment, the distance from you to the drone is decreasing. Well, if the distance is decreasing, that means the drone is getting closer to you. So I think the interpretation is at time 15 seconds, the drone is moving towards me or you at a speed of 10 feet per second. Okay. Speed, by the way, is just the absolute value of velocity. Okay. So if you have a negative velocity, the speed would be positive. So our velocity right here is negative 10 feet per second, and it means the drone is moving towards us with a speed of 10 feet per second. It's getting closer and closer to us, okay? So the sign on your derivative is important, and it's telling you something about the physical situation. If it's a distance function, a negative derivative means the distance is decreasing, and a positive derivative means the distance is increasing. And just think about the distance function. Increasing distance means positive slope, positive derivative. Decreasing distance means negative slope, a negative derivative.